Okay, we will get started. I hope you can hear me. So I'm going to start with the pre-lab for iodination of vanillin. So this general reaction is the same as the one we studied last Monday. It's electrophilic aromatic substitution. So last week we studied Friedel-Crafts acylation. This week we are going to study halogenation. Okay. In halogenation, there are different kinds. There's chlorination and bromination, which are more common. The reason for that is it's fairly easier, to handle chlorine and bromine. Chlorine, of course, is a gas, but still can be handled easily. And this one, of course, is a volatile liquid that are hazardous properties associated with the halogens that run through the family. But in terms of handling, it's possible. The problem with fluorine is it attacks glass, so all the glass must be Teflon coated. The problem with iodine is it requires a pretty high temperature to break it down. So it really, you have to go to temperatures using oil baths, like more than close to 300 degrees Celsius, and that is an issue. So we are going to look at a green iodination of vanillin that can be run at pretty low temperatures. So we're making it green by really dropping the energy requirements. We're also making it green by using a green solvent, and then a greener way of generating iodine. So the greener modifications, the major ones are energy requirements is minimal. And then we are using a green way of generating iodine. So we're going to use an in situ approach. The problem with iodine is it sublimes and settles all over the lab, and it can cause throat irritation, just like the other halogens. So generating required amount in situ, and then if there is any excess amount, destroying it right away is a much greener way. And then we are going to use a solvent, unlike last week's experiment, where we didn't use a solvent. We are going to use a solvent, and the solvent is ethanol, which is considered a green solvent, and then it is mixed with water, which comes with a bleach, that is another green solvent. So those are some main highlights of the reaction. Let's go to the equation itself. This is vanillin. So I want you to take a moment and just for your own practice, it's an exam coming up. What is the IUPAC name for vanillin? So we have 3 different functional groups on a 4th functional group, which is benzene itself. Apart from benzene, we have 3 functional groups. We have an aldehyde, we have an alcohol, and then we have an ether. So if you already looked at the Canvas scores for the lecture, I've given you the functional group priority. The aldehyde takes the number 1 priority. So this is going to be called an aldehyde, which makes this carbon 1. So this carbon is 2 and this carbon is 3. So at carbon 2, we have an alcohol. It's going to be a substituent and it's going to be called hydroxy. At carbon 3, we have an ether. It's going to be called methoxy. So we're going to say 2-hydroxy, 3-methoxy, benzaldehyde. This is the IUPAC name for vanillin. This is done mainly as a practice for you, okay? Because you got multiple functional groups, and we are going to get more into that. I don't say this is necessary for the exam 2, but it will be for exam 3. It's going to be treated with a couple different reagents. One is sodium iodide. Sodium iodide is the precursor to iodine. That means that's the one that's going to help you generate I2, from which you can get the electrophile. This is sodium hypochlorite. OCl minus is a hypochlorite ion. So this is hypochlorite, and that is the main active ingredient of bleach. Bleach is a solution. It's going to have the sodium hypochlorite dissolved in water. So the commercial bleach is usually 5% weight over volume. I could be slightly off. It could be 6%. So I'm going to take a quick look at it, but I think it's 5 or 6%. It's 5%. I'm going to go with the 5%. So ethanol and water are your solvents. So you're going to get an iodine on one of the unsubstituted positions on the ring. So change the color here and let's look at this. 3 different substituents. I want you to tell me whether an aldehyde, I'm talking about the aldehyde, is an activator or a deactivator. Is anyone? Aldehyde, activator or deactivator? So this is one of the questions that's asked. So that should be fairly straightforward. You should be able to say this. Is aldehyde an activator or deactivator? Very good. So that's a deactivator. What about an alcohol? Activator or deactivator? So I have the answer for the aldehyde correct. It's a deactivator. What about the alcohol? Yes, that's an activator. What about the OCH3? It's not a major difference here with these oxygens. They all have lone pairs. So I'm going to say activator. But we got a deactivator that's not going to control the orientation. We got two activators between the hydroxyl and the OCH3, which is a stronger activator, because the stronger activator is going to control where the iodine is going to go. Okay, so who is the stronger activator, hydroxy or methoxy? This definitely you should brush up before exam 2. So which is a stronger activator? Which one is going to control? Any ideas? So the hydroxy is a stronger activator. So write a little note for yourself. You have to know which is a stronger activator for exam 2. So if you take hydroxy, it's a stronger activator, so it's an ortho-para director. Both ortho positions are blocked. On one side, it is blocked by the aldehyde. The other side is blocked by the methoxy. So you can see how the iodine goes para to the hydroxy. Hydroxy controls the situation. It wins. It's the stronger activator compared to methoxy. Aldehyde does not control the situation here, does not control the next reaction because it's a deactivator. So you should get a very high yield. Typically high yields are 70% and higher for this reaction because you don't expect any side product here, okay? If there is any side product, it'll be a very minor product. So that gives you a little bit of idea on what these various components are for the reaction. As always, in an electrophilic aromatic substitution, the first thing we worry about is how to generate the electrophile. So generation of the electrophile takes place with this oxidizing agent. So we are using a strong oxidizing agent, but it's not strong like potassium dichromate. It is still strong, that is your bleach. So you don't see the sodium ion. The sodium ion is a spectator ion, so it is not drawn. So I'm going to erase that out. So that is your bleach. That's a hypochlorite. Iodide comes from sodium iodide. H plus is the mild acidic solution, and that really comes just by using ethanol. Ethanol is a mild acid. So we're not using any sulfuric acid, hydrochloric acid. We're using a relatively mild acid, which also doubles up as a solvent. That's ethanol. So this reaction takes place to give you iodine, chloride, and H2O. So what happens is, this is your oxidizing agent. I'll just give you a very brief idea of this. You've done this in Gen Chem. So iodide loses the electrons. So iodide gets oxidized to iodine. Loss of electrons is oxidation. So the oxidizing agent that brings it about is ClO minus. It gets reduced. And how do you know it gets reduced? There's loss of oxygen. Hypochlorite becomes chloride. So ClO minus is reduced. Loss of oxygen is reduction is reduced to Cl minus. So what we are looking at is a redox reaction. So what happens is when you add sodium iodide, ethanol, which is your mild acid, and your solvent, you add your bleach, a redox reaction takes place, iodine is generated. Iodine has kind of a purple color, so you will see this color generation within the flask. You will not come in contact with it. Okay, so iodine is going to be our electrophile, and that's how it's generated. So now we'll look at the mechanism of the reaction. So for the mechanism of the reaction, we're going to take our vanillin. So this time we will draw the pi bonds. We take the hydroxyl OCH3, then we have iodine. So what is going to happen is, first step, I'm going to use the corresponding pi bonds. I'm using the para position, the hydroxyl group. So I'm going to remove this. And then the first step is the attack of the electrophile. We have done this several times in this chapter, just revisiting it. These two pi bonds stay intact. So we're going to attach the iodine over here. We have hydrogen on each of these pi bonds. Remember that. You got a positive charge right on that. So the first step is a slow step, is the rate limiting step. We got water, which is relatively our base. We don't have anything stronger. So that's going to drop the proton here. This is going to be a fast step. This is going to be the regeneration of the aromaticity of this ring. So if you want now, you can go ahead and put the circle inside or keep the pi bonds. That's totally okay. All right, it's up to you. So I'll go ahead and get the pi bonds back there so you can see the generation. Then we got the I. So you have a hydrogen still there. This is your final product, and it's that simple. It is a reaction mechanism. Of course, that would be the generation of the electrophile. But these are your two steps of the electrophilic aromatic substitution. Please let me know if you have any questions here or if everything is clear. We can keep moving on. Typically, what happens is we tend to add a little bit extra of the sodium iodide and the bleach because we want to make sure there's enough concentration, a good enough concentration of iodine, so that we have a good concentration of the electrophile. And also, the other thing is your reaction may not go to completion. So the point I'm trying to say is you can have some unreacted iodine left over. So you have to take care of it. You want to get your pure product. Particularly with iodine, you want to get rid of it because iodine is also a staining solution. You might have used it in biology. We use it a lot in TLC at a little bit higher level. We will stain TLC plates using iodine. So it just stains everything and makes everything yellow or purple. So we don't want that. We don't want our final product stained with iodine. So we want to remove the excess iodine. So the excess iodine is removed by using sodium thiosulfate. Again, sodium is a spectator ion. So this is sodium thiosulfate. So you can see iodine now accepts the electrons. So iodine is reduced to iodide, which is colorless. So this is a deep purple color. This is colorless. So we are using a reducing agent. The reducing agent is thiosulfate, so that is going to be oxidized. So you can see additional oxygens here, and this is called tetrathionate. So this is after the reaction has occurred. After our desired reaction, we are taking care in the workup, we are adding thiosulfate to convert the unreacted iodine to iodide. In that way, we can get rid of any stains the iodine might, stain the final product, or just it's a pretty heavy molecule. It may increase the percent yield. So we're taking care of all of that by getting rid of this. So that's an important chemistry that happens in the workup. Now I want to show you how simplistic this reaction is. You're going to take an ice bath. We typically use an ice bath, keep the temperature low. That's a remarkably different condition from regular iodination, which usually requires a very high temperature to break down and give iodine. In the reaction mixture, we're going to take vanillin, we're going to take sodium iodide, and then we're going to take ethanol and water. The ethanol helps dissolve the vanillin, whereas the sodium iodide is dissolved in water. Because we got a polar sodium iodide, we have a relatively non-polar vanillin, we tend to use a mixed solvent scenario. On top of it, ethanol provides a slightly acidic solution. In the burette, you got bleach. We typically use Clorox, a commercial bleach, which I think is 5 or 6% weight by volume. So that's what drops. So you will do this reaction with a very slow drops of the bleach. You don't want to bring the concentration of the bleach very high. The reason for that is you don't want to have a sudden increase in the concentration of the iodine. If that were to happen, you will run into this problem. You have two activators on the ring. So we have the aldehyde, we have the more strongly activating hydroxyl, we have this. If you increase the concentration of iodine very quickly by adding bleach really fast, then the methoxy can also jump in, because that's also an activator, and that is a strong activator. Hydroxyl just turns out to be stronger. So you can get this product where you can get the iodine ortho to the methoxy and para to the methoxy. You can get it on the same molecule, or you can get two different molecules where the iodine goes para to the methoxy. So instead of getting one pure product, you'll get a lot of contamination. To avoid that, the slow addition of a bleach is absolutely necessary. During the addition of bleach, colorless can change into a purple color, and as the reaction continues, it can become green. Okay, there are some color changes that occur, but you will see the generation of iodine and the slow disappearance of iodine. A little bit of a green color stays back, and then we do a workup. In the workup, you expect your final product, which shouldn't be this. It should be a very pure iodinated iodine. It's going to be contaminated with sodium iodide, a little bit maybe unreacted reactant. It could have a little bit of bleach. It'll definitely be contaminated with ethanol and water, and we have to take care of all of that. And you will have maybe even some iodine just floating around there. So you're going to take care of the iodine by adding sodium thiosulfate. When you add water and do the Buchner filtration, you'll remove the sodium iodide, and any extra bleach will simply go through the Buchner funnel, the Buchner funnel, and you'll take care of all of that. So typically students get a very pure product of this iodinated vanillin. So that is with the experimental aspect. Any questions so far? Anything you want me to repeat? We'll discuss more chemistry as we look at the pre-lab and post-lab, but I do have some data that's generated for you. It's pre-generated data. You'll find this in Canvas. You'll find this in the lab procedure. So you want to go to the last page. The last page, you'll see the same exact table. Everyone is going to use 1.0015 grams of vanillin. It's a 1-to-1 reaction. You have sodium iodide, ethanol, bleach. So you have three reactants that you want to consider, and you want to find out which one is the limiting reactant. Orthovanillin is one, sodium iodide is the other, bleach is the third one. Okay, so you will calculate theoretical yield using all of these things. So what I'm saying is you will set up three calculations. That's what I'm saying. You'll start with mass of orthovanillin times 1 mole vanillin, right? And then you want to get the molar mass of vanillin. I have it written down here. I'll give it to you, but you can find out as well. So fairly straightforward setup. 152.15 grams times, it's a 1-to-1 mole reaction, so 1 mole vanillin, and then you have 1 mole, this is iodovanillin, that's what I'm going to call it. Okay, and then you can get the molar mass of iodovanillin, which is not difficult to obtain, but it's pretty high. I don't think I have that. So 1 mole iodovanillin. So I just looked up Fisher. It's 278.04 grams. So this will give you a theoretical yield of iodovenylin based on orthovenylin, you will repeat this calculation with sodium iodide. It's again, okay, you want to repeat the calculation with sodium iodide. All right. Now, the last thing is you want to repeat this calculation with bleach, and that's what I want to talk about. So I'm going to assume bleach is 5% weight by volume. If it turns out 6% weight by volume, I think I've given it in the procedure. You just change it, change the 5 to 6, but that's what it is. So I'm going to say it is 5.00% weight by volume. What that means is 5.00 grams of sodium hypochlorite has been dissolved. Let me rewrite this. This is 5.00% weight by volume. That means 5.00 grams of sodium hypochlorite has been dissolved in 100 milliliters of water. Okay, that's what it means. In order to find the moles of sodium hypochlorite, we need to get to the molarity of bleach. I'm sure you can handle this, but I thought I'd just go over this. So I want to convert this 100 milliliters into 1,000 milliliters because molarity is in liter. So I want to multiply it by 10. So that'll be 50 grams over 1,000 milliliters of water. Okay. So I'm going to take 50 grams, right, in 1 liter, 1 mole, and sodium hypochlorite's molar mass is 74.4 grams. That should give you the molarity because grams will get canceled. You remember this calculation, you guys? You've done it many times. Moles over liter, which is nothing but molarity. Okay, grab my calculator here. Let's get the molarity. So we get 0.672. So that's the molarity of bleach. You need that because you're told you're using 12 milliliters of bleach, right? Remember that? Now, from the molarity and the liters, you can get the number of moles because you know molarity equals number of moles over volume in liters. So molarity is 0.672. You can get the moles. You can use some unit analysis. It works really well here. 12 times 10 power minus 3 liters. So that'll give you the moles of bleach. Okay. So you need the moles of bleach because you need to calculate, you need to take the moles of bleach times the molar mass of the product, which is 278.04, and get the theoretical yield. Am I making sense? You need to get 3 theoretical yields from 1, 2, and 3. 1 and 2 is not a problem. You've been doing this for a while. 3 is not necessarily a problem, except you have bleach and you don't have the molarity, you only have the percent weight over volume. I'm making this 5%. If it turns out to be 6%, just change your calculation, but this should kind of set you up for getting the molarity. Okay, I'm going to pause here. Let me know when you can, when you're ready, okay? If you have any questions. Okay, so that will be for your theoretical yield calculation. Your product is 1.393, so you'll use that divided by the theoretical yield times 100. That'll give you the actual yield. All right. Then we're going to look at some spectroscopy, and then we'll move on to your pre-lab and post-lab, and most questions are answered in this discussion here. So this is your vanillin. 2 kinds of vanillin. That's this one is called orthovanillin. Okay, so let's take a look. We want to assign the peaks. How do we distinguish this from our product, which is our iodovanillin? So we have, I want to say this is HA. This is our methyl group. Okay, this one I'm going to say is HB. That's our aldehyde right here. Call this HC, which is right here. Then all of these I'm going to say is HD, which is right here. out of which we have 2 doublets and a triplet. It's not very clear, but we have a triplet right here, and this is 2 doublets that are overlapping, but we have them all there. We don't have to distinguish them. That's the aromatic region, as it's very clear. Now that should integrate to 3 hydrogens. The key thing here is this same aromatic region will integrate only to 2 hydrogens, and you should see 2 singlets, and that's what you see, 2 singlets right there. So I'm going to say A and B. So let's see, this is B and this is A, because iodine is also deactivating, aldehyde is deactivating. I'm going to put that as more deshielded. I'm going to call this C. This one is D. This one is C. This one is, these are your standards. That's your TMS, tetramethylsilane. That's your standard for telling the computer to mark that as 0, because everything is relative to that standard. If you mark that at 1, all these chemical shift values will change. So you should see a nice separation. The key thing is the 2 singlets, but one is more deshielded than the other. Will be a clear indication. On top of it, students get a very nice integration of 2 hydrogens and 3 hydrogens. So proton NMR can be used to distinguish the product from the starting material. Our carbon-13 is usually our confirmation tool, but we're going to look for the main confirmation here, which is the aldehyde carbon, which is right here. That's the one. Our CH3 is right here. Then all your other benzene carbons are right here. So you don't have to distinguish those. They're not really useful. What is really useful is our aldehyde. So you can see that it doesn't really help out with identification of the product. A lot of times carbon-13 won't. Carbon-13 is more a confirmation. It's add up. That's all it is. It's not really telling you how to confirm the product. It's, it just gives you a little bit extra information which you may use or not. Now, again, you see the aldehyde proton, right? Aldehyde carbon right here. This is carbon-13. This is CH3. Okay, that's really important. So now we have hydroxyl and iodine. Iodine being the deshielding one, you will see that here. This is your carbon iodine. And these are all your aromatic. So not a very strong tool, but still gives you the peak, see that new peak, which is absent here. So when you compare, it does help. So you have that carbon that's connected to the iodine up here there, because that's deshielded and it's, coming separately there. You might wonder why it's not more deshielded than the other carbons here. The other carbons are the benzene carbons. Why they can be more deshielded, that's a different effect. They all cluster in the same area. It's the new peak that gives you the difference. That's a carbon iodine, and that's where those come. It's not like iodine is so deshielding. It's not really that electronegative. If it were a fluorine, it might have pushed it even beyond 150, and you might have seen it there. Iodine is somewhat electropositive itself. It's not that electronegative. That's why it just comes at 90. In case you're confused as why it's not getting more deshielded than the other carbons, it's not that electronegative to push it way down there. So those are your carbon-13s. So that's all I have with pre-lab. You should answer many important questions in your, in your pre-lab and post-lab documents, which you have to answer. So if you have any questions, let me know. If not, what I want to do is start with the pre-lab assignment, and then you can make a note of your questions. Also ask me later. That's fine. We will begin with this. This one is, if you've already turned it in, actually only one person did, you can turn it in again. So we did talk about this. The general type of the reaction is electrophilic aromatic substitution. right? I gave that to you. The specific type of reaction is halogenation. You have that in the pre-lab lecture. Hopefully everybody's good with that. So iodination is difficult to carry out for a number of reasons. One, requires high temperature to generate the electrophile. Iodine sublimes, handling iodine is difficult unless you come with a method of generating it in situ, right there. You don't want to pick crystals of iodine and add it. That's usually somewhat difficult because as you're adding it, some of it will sublime. You'll be surprised that your gloves, a lot of glassware will have a purple tinge. So handling iodine is difficult because of the sublimation. So this should be ring. Name the substituents on the vanillin aromatic ring. So we talked about this. You have the aldehyde, which is deactivating. All deactivators are meta directors. I didn't hear too much from you guys on this. You must know this for the exam. This is big. These are activators and orthopara directors. So possible side product of the reaction, you may have to capture an image and upload it. So let me just jump to this. The possible side products, there are two of them. That's basically if you don't do the job well. If you did the job well, you shouldn't have this problem. You should get nice, good 70, 75% yield of this product. But if you increase that electrophile concentration very quickly, a lot of students even fail the reaction if they did that, is you could get this methoxy to start activating the ring. So that'll be one product, ortho to the methoxy. This is very simplistic. This could be para to the methoxy. So you could get these possible side products. Typically in our lab, we don't encounter it because we're very careful in getting that bleach going dropwise. And then we stir it for an hour to ensure reaction has taken place at 0 degrees. We don't increase the temperature. If you increase the temperature, the less activating OCH3 can start the reaction. Okay, that's why you keep the temperature low as well. So only the strongest activator will control the reaction. The OCH3, which itself is a strong activator, will not be able to take over. What is the role of bleach? Equations are not necessary. So you're going to say bleach is an oxidizing agent. It is a reasonably strong oxidizing agent, but you know what? I will say moderately strong because it's not as strong as potassium dichromate. That oxidizes iodide to iodine. This is how the electrophile is generated for the substitution reaction. So the role of the bleach is in one way generating the electrophile. It does it by oxidizing iodide to iodine. I've given you the equation for that. It's not necessary to write it. What are some advantages, synthetic advantages of introducing a halogen? Why go through all this trouble to get a halogen on the aromatic ring? So any ideas, anyone? We have done this. So what is the reason? So we don't have to get too technical here, but we will still draw the final product. And what are some ways this is going to be useful? Okay, anyone? I can give you the answer, but do you want to just like chime in a little bit and I can use your idea and build something? I mean, you got, yeah, it's an orthopara director. Very good. But it's going to have a lot of problem. You won't be able to get a ring. You won't be able to get a substituent here. That'll be between two substituents. You won't be able to get a substituent here. It's between two substituents. In this case, it's a problem in general. So if you want to use that, Samantha, you don't want to use this product. Just use a regular iodine and say it's an ortho-para director, so it can be used to introduce groups ortho and para. You don't want to use this particular structure because this particular structure, the iodine, is an ortho-para director. It's quite useless because it cannot get groups between groups. So you don't have to use this final product. You can just use an iodine on the benzene and say it's a useful ortho-para director. And I'll take that. That is a synthetic value. Okay. So if you guys want to keep it very, very simple, you can do that because you won't have too many disadvantages. So that is one thing. I'm going to take that. Okay. Orthopara director. So I'll say that if I get an electrophile, I can get it ortho or pair and para. Okay. So I'm not really drawing the product. This kind of explains what that means. Any other? I'm going to give you a little clue here. Okay. Then you can build up. I'm going to add magnesium, the presence of ether. What is it I'm going to make? Now you guys should tell me. This has synthetic value. This is an important reagent. I add magnesium to this. What do I get? Very good. We get a Grignard, and you can use a Grignard for a number of things. So Grignard is high synthetic value. You don't have to say what you can use the Grignard for, but you can use it to make alcohols, you can use it to make carboxylic acids, and you just have a lot of uses with the Grignard. Okay. Or you can also say lithium. Those who don't want to say magnesium can say lithium and say you make an organolithium. Nothing wrong with that. So I'm going to use the iodine. Okay, this is the alkyl iodide. And then I'm going to add copper iodide. And then I'm going to, basically my goal here, right? So I'm going to, first step, I'm going to add lithium. Second step, I'm going to add copper. You can add copper iodide, or you can add just copper to carry out the reaction. But what you get out of this is this. What is this reagent? So your idea is really convert this. You don't have to write very elaborate things here. Convert to, what is this reagent called? That was Grignard. What is this? This is another very useful reagent, Gilman. So this also has great synthetic value. Okay. So there are three. And if you can think of more, you can certainly write more. It's up to you. But the alkyl iodides, introducing an iodine is very useful, and you can use it for a number of reactions. What you want to avoid is SN2, E2. Those are not possible, so do not use those. That would be wrong answer. Okay. Okay. There are a few more, like nucleophilic aromatic substitution. You could certainly use that. It's not just restricted to the three that we have there. Okay, that completes your pre-lab. All right. Any questions on the pre-lab? Okay, I'm going to open your lab assignment, which has a few questions. So you have what is the role of bleach. Here, I like you to include the reaction, and I've given you the redox reaction. So include the reaction here. Say it is an oxidizing agent, and include the redox reaction here because you now know more because this is your lab report. Okay. Electrophile and nucleophile in today's reaction, you should be able to say that. What is the nucleophile? I'm going to write the electrophile here. Iodine. What's the nucleophile? Okay, I have 3 students today, Samantha, Arja, and Sophia. Anyone else? You know this. You just don't want to answer this. This is orthovanillin. That is your main nucleophile, right? The benzene ring is your nucleophile. So orthovanillin is a nucleophile. How is the electrophile generated? Right equation. So you do have the equations. How it's generated. So it's somewhat similar to question 1. And then once you have that ionic equation written, you may want to write the first step, or you don't have to. You can just show how that iodine is generated. Somewhat similar, question to the first one. Yes, the main constituent in vanilla is vanillin. Yep, that is the reason. And that bitter taste in almonds is from benzaldehyde. That's from the aromatic compound. Yeah, it's very any derivative of vanillin will have the smell of vanilla. So your artificial essences are created the same way. You have the mechanism of the iodination of orthovanillin. I'm also recording this and I've written it down, so you should be able to do this. Explain regioselectivity of orthovanillin. The only thing I want to add here is the resonance structure. So we'll talk about that. So the regioselectivity is you will go para to the hydroxyl group, and that's what we want to know, right? And we want to support that with resonance structures. We didn't talk about resonance structures, so let's do that. And that should give you the added information for this particular question. So you want to talk about regioselectivity. You want to say that hydroxyl is the strongest activator, and therefore the iodine goes para to the hydroxyl because both ortho positions to hydroxyl are blocked. You want to start off your answer with that. That explains the regioselectivity as to why something goes here. These 2 positions are blocked, and this hydroxyl is your strongest activator. Now we will go ahead and draw resonance structures. So for resonance structures, what we are going to do, let's see. I'll have a double bond here, I'll have a double bond here, I'll have an iodine here, I'll have a hydrogen here, I'll have a positive charge here, okay? So that is your intermediate. You have to start with that to explain the resonance structures, all right? Now what we want to do now is draw resonance structures, which means we're going to move this pi bond that's closest to it. We want to show the stabilization of this intermediate by moving this pi bond towards the positive charge, and then you'll get a positive charge on the oxygen. Now what you want to do is use the lone pair and move the lone pair. You can see that extended. Now you see why oxygen hydroxyl is an ortho-para director. See, this particular one shows how hydroxyl, being an ortho-para director, is an activator. It's sending its lone pair inside. You have to show that via the resonance structure. So I'm going to write an explanation, I'm just going to label the structures 1, 2, and 3. Then I'm going to say in structure 2, extra stabilization, right? You do have extra stabilization is offered via resonance by the hydroxyl group. Or you can say a hydroxy group. This further ensures that iodine attacks the position para to the hydroxyl group. So that's what I've done here. This position is para to the hydroxy group. If iodine were to attack para to the hydroxy group, you will be able to draw this resonance structure too. So this is going to be your support using resonance structures. The important thing is you have to start with this intermediate. You don't start with the molecule. You actually have the iodine, attack the para position, and then explain why that is favorable. It's favorable because you get that extra stabilization of the positive charge right here by using that lone pair on the hydroxyl. If you attacked it meta or any other place, you cannot attack it ortho because your aldehyde and methoxy are blocking it. If you took it to the meta positions of the hydroxyl, you won't be able to get this resonance structure. We don't need to show how we will not be able to get it. We'll just go positive here with the answer and say how we will be able to get us extra stabilization, which is resonance structure 2. Okay. We'll be able to offer that. So that should kind of conclude your answer. But to begin with, you want to say hydroxyl is the strongest activator, therefore controls the incoming iodine, by sending it para to the hydroxyl group. It goes para to the hydroxyl group. You do want to talk about that regioselectivity and then start off with your resonance to explain this. Okay, bring that on the screen. Any questions, please let me know. OCH3 doesn't leave. I just forgot to write it. It does not leave. It's very much there. Thank you, Yumara. You never substitute for the pre-existing groups. You'll only substitute for the hydrogens in electrophilic aromatic substitution. Substituting for pre-existing groups is the lab next week, not this one. Okay, so good question. So keep that in mind. So that will be that question 5. Role of sodium thiosulfate, you're going to say is to neutralize. I'm just writing hints here. Please write complete sentences. Neutralize unreacted excess iodine. And I do have that equation for you. It's in the PowerPoint presentation as well as in the recording. Now, why is the product mixture acidified with HCl? So in your workup, what you do is you acidify the product mixture. So as I mentioned, once you're done with the reaction, you're going to have the product, which is this guy here. You could have some extra iodine. You're going to have ethanol. You're going to have water, right? You can have all of this. And usually there is no side product contaminating it if you allow the reaction to go slowly at 0 degrees. But what you do now is you add dilute HCl. You take a look at the product, you got a hydroxyl group. The product is slightly acidic. So if you add an acid, the product will be insoluble in the acid medium. Acids don't dissolve in acids. The OH ensures the product is slightly acidic because hydroxyl is an acid. Okay, so product will be insoluble in dilute HCl. What will happen is it will not, if it does stay dissolved in ethanol, product is soluble in ethanol. Okay, so you have to bring it out. Only if it is insoluble, you can do a vacuum filtration and filter it out. So at the end of the reaction, you get a solution. You don't have a product. You have to somehow precipitate it. So you know the structure of the product, you know the product is slightly acidic. So what you do is you make that medium acidic. You keep adding dilute HCl till the pH becomes acidic. The product will be insoluble in dilute HCl. This will precipitate the product as a solid. So S is a solid. Okay. Because when the reaction is done, your final product is going to be soluble in ethanol. If you want to say that also will be fine. When the reaction is completed, iodovanillin remains soluble in ethanol. Dilute HCl is added. The product will be insoluble in dilute HCl. This will precipitate the product as a solid. I think that'll give you a nice complete answer. So what was soluble in ethanol now becomes insoluble in dilute HCl. You precipitate it and you can filter it and you get a solid product. Is everybody clear on that? So I've assigned the peaks for you. Please take a look at it. You could label it any way you want. I just randomly labeled it ABC. But you can assign the peaks. That shouldn't be a problem. You can calculate theoretical and percent yields. You should have 3 theoretical yield calculations, one based on orthovanillin, one based on sodium iodide, and one based on the molarity of the bleach. I hope all of that is okay. I didn't mean to just scroll through that. We discussed all of this, so I hope you can do that. And then our last question is we're going to use 12 principles of green chemistry. If you want to know what the 12 principles are, you just type 12 principles of green chemistry and I'll give you all the 12 principles. But I've given you some hints. You can use these. I'm not saying you should use all of them, but let's go over this. And I'll tell you how to work with this. The first one is toxicity. Okay. So you want to see if any of the chemicals are toxic. So what I'd like you to do is refer to SDS. SDS is safety data sheet, and it's fairly simple to do. You can just go to Fisher. Any company that sells these chemicals will do it. You don't have to check everything out. I want you to check orthovanillin, see if it is toxic. I don't think it will be. You don't even have to because we use it, but you can just check it. And then I want you to check sodium iodide. Then I definitely want you to check bleach. You're using a little bit of hydrochloric acid, but it's a small amount. If you want, you can check that. But these are your 3 main reactants: orthovanillin, sodium iodide, and bleach. Check for the toxicity. Of these, I expect some toxicity to be involved with bleach. Okay. Then the environmental impact. So this one, you want to look at the side products that are formed. Our side products that are formed are typically soluble salts. We really don't have anything noxious here. It's really just the soluble salts that are formed. So you should not have any major impact. Reactivity, nothing is flammable. Okay. So you should have no flammability issues. Solvents required for the reaction. Yes. You need 2 solvents. You need an organic solvent, which is ethanol, and you need an inorganic solvent, which is water, because you do have sodium iodide, which is inorganic, will dissolve in water. Organic will dissolve the vanillin, which is your starting material. You don't have to purify any solvents, so no purification of solvents is required. So I'm actually writing these down and I'll bring it up for you in just a second. So atom economy of the reaction, the way that's calculated is the number of atoms. So it's fairly simple. How many atoms do you take and how many actually go into your product? So what you do is you take the formula weight of the product divided. Formula weight is nothing but the molar mass. Okay, if you want to say molar mass of the product, that's fine. Divided by molar mass of all reactants. You don't want to just take vanillin, all reactants times 100. So let me just show you a little bit on that. So what I've done is written down some points here. I don't want to be on that. Okay. So what I have here is written down some points. Toxicity, I want you to refer to SDS. Environmental impact, all you have is soluble salts, so you want to say minimum environmental impact. I don't see any flammability issues. You do have two solvents, both solvents are green. Water is pretty innocuous. Ethanol is not bad either. You don't need to purify any of these. Now, what you want to do with the formula weight is you want to take the molar mass of the final product. I think I gave it to you. Molar, that's not a problem. So your final product is iodovanillin. You take the molar mass. And then I want you to take all reactants, which means you will take vanillin, sodium iodide, sodium hypochlorite. You need to take all these three reactants. You take the molar mass of all of them times 100. Okay, look at the percentage. If you get 80% and higher, it's atom economical. That means 80% of the atoms have gone or higher have gone into the product. So I would say the reaction is atom economical. If it is less than that, if it's like 75%, it's moderate. But if it's really less, really low percentage, it's not a green reaction. You're wasting a lot of atoms. Majority of the atoms don't go into your product. They're going into your waste. That's what it means. So is this making sense? So percent atom economy is calculated using this formula. The catch here is you have to take all reactants. So all our you don't have to take solvents, but you have to take all reactants. That would be vanillin, sodium iodide, and sodium hypochlorite. So when we analyze a reaction using green methodologies, something we need to do. So I took those different points there. There are 12 principles. Just created some parameters that you can use. Next, we have reaction time. So go ahead and read the procedure. You'll find the reaction time is a good 1 to 1.5 hours. That's not a fast reaction. So it does take quite some time. It's not like 10-minute reaction. You are spending some time there. Reaction temperature is going to be 0 degrees Celsius, which is not difficult to attain. It is not room temperature. It's not very ambient, but it's not bad. You can achieve, it's not minus 78 degrees. It's not difficult to get that. Okay. Ease of separation, that's really up to you. If you think adding hydrochloric acid, doing a vacuum filtration, all of that is tedious, then you make your comments. There's no right or wrong, but I would say it's not contaminated with any of the site products. I don't expect any site products, so I don't expect, any major chromatography or recrystallization. I don't expect too much, of separation there. So I would say it's fairly easy. But if you think that you have to work hard and doing a Buchner and acidification, checking the pH, make your comments. Energy requirements, in my opinion, 0 degrees is not bad, but it's not room temperature. Purity of a product, it really depends on the melting point. You can skip that because you're not determining the melting point. Side products, as I said, we don't get many side products, not very hazardous. Glassware setup is your comment. Ease of cleaning is your comment. If you got fractional distillation, it's not easy to clean. You've got like 20 pieces of glassware that you need to clean. But I don't think, comparatively, it's not bad. So a lot of these things here, like 9, 12, 13, and 14, I'm just going to leave it to you. You can make your comments. But these are some factors that you take into account and you can explain how green this reaction is. So finally, you want to draw a statement, write a statement there, draw a conclusion on whether you think the reaction is green or not. There is no right or wrong answer. Okay, so if you don't think the reaction is green, fine, go ahead and say it. You're not going to lose points. Okay, just gives you a way that American Chemical Society would like you to analyze labs in terms of greenness. It just keeps you current with that and explains that to you. This question just addresses that. Okay. So I want you to take a good look at everything. I think I've covered everything reasonably comprehensive. If you feel something is missing, please let me know. I'll cover it now while the recording is going on. If not, both the pre-lab and the lab are due next Monday by midnight. So take a look at that and let me know if you have any questions. If not, you're free to go. I don't think there's any need to return. We will not start Spartan until next Monday, okay? So we have finished the Spartans on aromatics. We will be starting them with aldehydes and ketones, but that will be only next Monday. those who like to work ahead, the modules are open and more things will be open. Yes, this is it. And then starting from next week, everything is on LabFlow. Yes, I will get that, NMR. This is your LabFlow didn't have any experiments on electrophilic aromatic substitution. That's why I had to get it in Canvas. However, they have an experiment on nucleophilic aromatic substitution, which is next Monday. We are back in LabFlow. Everything else is in LabFlow. So let me get to. Okay, I will keep scrolling this, scrolling through Samantha, let me know. And that's it for today. You don't have to return unless you have any questions. You can stay back, but I'm gonna just turn off quickly the recording. So, and then bring the screen back on full.